Good afternoon to everybody. My name is Miguel Sabogal and I will present my work titled as Cosmological Analysis of Barrow Holographic Dark Energy, considering the Granda-Oliveros infrared cutoff. The advisor of this work has been the Dr. Alexander Oliveros, associated to the Universidad del Atlántico. The content of this presentation is structured as follows. First, an introduction, our results, and finally the conclusions. As many of you may already know, in 1998, the accelerated expansion of the universe was discovered for the first time. This was achieved to the standard brightness of this type of supernova, type 1A. In this figure, it can be seen how the larger the magnitude of the redshift, the fainter the object. And this figure represents how the expansion in the early epoch is accelerated. This acceleration is attributed to the existence of a mystery component, as you may know, that have a negative pressure, which has been called dark energy, representing approximately the 68% of the content of the universe, according to the last observations of Planck. This acceleration expansion is reaffirmed by studying the anisotropy observed in the CBM, studying the LSS and Barrow. The discovery of this accelerated expansion is one of the bases of the current cosmological model, as you can see in this figure. This model is the lambda CDM model. Lambda stands for cosmological content, as you already know, which is the simplest candidate to represent the dark energy. However, this cosmological content presents huge inconsistencies with the fitting problem and the coincidence problem. Besides the cosmological constant, different models have emerged, as can see in this picture, with proposals to explain the nature of dark energy. Perhaps one of the most transcendental is the known holographic principle, and it's which we are going to focus right now. Okay, the holographic principle holds that our three-dimensional world is a hologram or a projection of all this activity taking place in a two-dimensional surface full of qubits or information. That's it, that the entropy of a system increases with its area and not with its volume, as the vacancy-Hawkins entropy for a black hole. As you can see in this picture, that is a schematic representation of the holographic principle applied to a black hole, where this is the vacancy-Hawkins entropy for a black hole. By applying the holographic principle to the cosmology, can be obtained an upper limit to the entropy that it's contained in the universe. Together with the fact that in a quantum field theory, a short distance is related to a long distance cutoff. It is established with these two assumptions that in a cosmological context, a system with size L and ultraviolet UV cut, the energy density in that region does not exceed the mass of a black hole of the same size, L. Taking the largest value of this L, this inequity is saturated and resulting in this, that is the holographic dark energy density. Recently, Barrow, inspired in the COVID-19 virus, demonstrate that the quantum gravitational effects can introduce fractal features into the surface of a black hole, as can be seen in this picture. That is a diagram taken from this paper of Barrow. And therefore, these quantum gravitational effects lead to a deformed black hole entropy, quantified by this parameter, the deformation parameter, where delta equals to 0 is the standard vacancy-Hawking entropy, and delta equal to 1 is the more deformation case. Applying this holographic principle in a cosmological scenario, using Barrow entropy, and Sheridansky obtains extended holographic dark energy that includes the basic holographic and dark energy as a subcase where when delta is equal to 0. The peak of an infrared cut in our models plays a crucial role in the behavior of the model and its consistency. For example, if the cutoff is taken as this one, the fitting problem is solved, but this not reproduced as an accelerated expansion regime. As the same case occurs with the particle horizon. When it's considered the future event horizon as the cutoff, there is the causality problem due that this cutoff depends on non-local quantities and present that problem. With the intention to solve this problem, Granda and Oliveros proposed this new infrared cutoff, introducing this new quantity, solving the causality problem and reproducing an acceleration expansion regime. In our models, we are taking account first of all the Einstein field equations, the Freeman-Robinson-Walker metric for a flat universe. We are taking the content of the universe at large case as a perfect fluid. These cosmological parameters we are taking as the last one for Planck. We are considering the Barrow holographic dark energy, and finally the Granda-Oliveros infrared cutoff. Taking all these into account, the Freeman equation of the model were obtained, where this is the first one. Solving this equation numerically, we obtain the next results. Here it can be observed how delta, the deformation parameter, affects the values of the whole parameter in relatively low redshift. In this graphic, beta and alpha were fixed, and in the inside figure is a sum of the same function plotted, but at these values. Taking in this picture, this figure of the whole parameter of the model for a high redshift compared to the lambda CDM model. In the inside figure, it can be shown that as delta increases, the difference with respect to the lambda CDM models decreases for the different values of delta. In this graphic, we present the deceleration parameter that is in terms of the Hubble parameter, and it can be seen that for the different values of the delta, there is obtained an accelerated expansion regime, and it can be seen how it affects the redshift transition from decelerated to accelerated.
You have 5 minutes.
Thank you. In this graphic, the deceleration parameter was varying with the parameter b, and it can be seen how it how significantly affects the present value of the deceleration parameter and the zeta transition. As the same in this graphic variating alpha. In this graphic, we variate delta again, and we plot the equation of state of a parameter of dark energy, and we can see for the Mott's value is less than -1. For varying alpha beta, also we found that this behavior is changing now. The more than when beta increases, the values increases. And for alpha, we found that these values show the more flashy characteristic of this model is that it can be located in the quintessence regime above -1 or above in the phantom regime. Here it's plot the speed sound of square multiplied by its signs in a logarithmic scale as a function of the redshift for different values of delta. This quantity represents the stability of the model. It can be seen that for the more values of delta it remain positive. This is stable, and for one value there is a zone of instability, representing that in these values the speed sound of square is negative. Finally, in this plot we show the evolution of the densities involving in the model for different values of delta, where it's observed that the model achieves an area of radiation dominance, as can be seen here. An area followed the dominances by the non-relativistic matter, and the current era of dark energy dominance as the present. Finally, in the conclusion was in our model for a Barrow holographic dark energy, considered the Granda-Oliveros infrared cutoff, it is possible to obtain a regimen of accelerated expansion. We also see that this is a similar behavior with respect to the lambda CDM model, at least a 1.5% in the Hubble parameter values. As well, beta and alpha parameters, the deformation parameters significantly affect the values of the redshift transition and the values of the equation of the parameter. This model is stable on the perturbations since the early epoch to the present. However, it presents a zone of instability. And finally, the model achieves the era of radiation dominance, followed by the non-relativistic matter and the current energy dominance. As a future work, we will adjust the model parameters using the current cosmological data for these new three parameters. And we pretend to study the phenomenology of this model using the well-known program class in collaboration with the present Dr. Wilmer Cardona as a future work. Thanks to the viewers and the host, and happy to answer the question if there are any.